All right. How's everybody today? I'm going to start right at the hour just because of all the content that we're going to be covering today. So just very excited for today's live event. Welcome everybody. My name is Greg Paulson. I'm from Xometry, and I'm excited to talk to you today about advanced tips for CNC designs and drawings. So before we start though, let's lay down a little bit of groundwork. We're going to begin with introductions. We're going to tell you a little bit about Xometry, what we do and how we do it. And then we're also going to go through the nitty-gritty of the CNC advanced tips, technical drawing tips, and quoting special requirements and other things that make drive cost and may merit that conversation along the way. Our goal today is to walk you through CNC machining design principles. So common features, what drives cost or complexity, some tips on communicating intent with your drawings, making great technical drawings, and I'm bringing on my co-host, Steve Zimmerman, who is an expert machinist and toolmaker to help guide us along the way as well. Uh, So our team at Xometry, we talk from our experience on working on thousands of projects from every industry you could imagine. We love answering questions, and I always encourage you to use that Q&A tab in the Zoom webinar box there and ask questions along the way. We're going to save time at the very end. My colleague Megan's going to help us through some of the Q&A session at the end here. But please ask questions along the way, and we'll try to get to as many as possible at the end of our webinar event here. And I'm really excited about that because we love context. Where I think Steve and I are professional question answerers at this point, so that's what we like to do the best. And of course, this webinar is also recorded. So we're going to have a recording of this webinar on a blog post. It'll be posted a few days after this event. And along with that, I'll try to answer some of those Q&A and common topics that we see in that blog post as well. So you'll have something to reference to and share with your colleagues. So let's introduce the team there. So I'll start with myself here. My name is Greg Paulson. I'm the Director of Applications Engineering here at Xometry. I work on a lot of projects across a lot of disciplines, talking about design, spinning CAD with our customers, looking at technical drawings, helping customers figure out, what process to choose and when. My background is over 15 years of advanced manufacturing, started in industrial additive manufacturing. But over the years, I've expanded working with people like Steve in learning things like machining, sheet metal fabrication, injection molding, and I love just being a sponge for manufacturing design principles. And yeah, along with me here is Steve, who is an expert tool maker, 30 years experience, a machinist, and you are a senior partner support specialist at Xometry. And Steve, tell me a little bit about what that means. What is a senior
Yeah,
support
so
specialist?
yeah, so I help our partner network with any kind of issues they run across in machining or applications engineering when it comes to CNC world. I also help onboard all our new partners coming into the network.
Yeah, and that's something really exciting. So Steve is there working with our suppliers, our partners, as they join the Xometry network and are taking and producing work and working them through their first jobs. Because beyond just making parts, right? We are a digital manufacturing platform, and guiding the suppliers through gives the best experiences. It's great experience for you, our customers who are designing parts and looking at parts, to quality and on time. And it's just terrific feedback loop that we have here. So, like I said, I have a lot to cover today, lots of topics, and this is something that people ask about so much. So we wanted to put a dedicated webinar to this. So let's just jump in and get started. Uh, I'm going to start with what we are. So who are these guys talking to you? What do we do? What is Xometry? So we are a digital manufacturing marketplace. We serve nearly 60,000 customers in making custom manufactured parts on demand, offering over 20 different manufacturing processes, and we do this through a digital platform experience. We are a two-sided marketplace, which means that we are connecting both the buyers, customers, those who need things made, and the suppliers, or as Steve says, like the partners who are producing those parts all throughout a digital platform experience that is Xometry's. We are publicly listed as XMTR, and we offer full manufacturing services, and we're global. So Steve and I are reporting from Xometry North America, but we also have a European division as well as an Asian division. So we're just slowly conquering the world, is what I'm trying to say there. And our manufacturing landscape is pretty vast. over 20 different manufacturing technologies. Bread and butter is going to be, machining, sheet metal fabrication, sheet cutting, and additive manufacturing. And then we have the formative processes to help you scale from where you are in a product development process to where you want to be in sustained production, or wherever you are in that product development journey. We're here to meet you. So injection molding can be bridge tooling or full production tooling. We do die casting services, plastic metal extrusion, metal stamping, in other formative ways. And on the fabrication side, if you're using, bent tube, laser cut tube, sheet cut, water jet, laser cut, all that is within our capabilities as well. So really, truly a one-stop shop. Xometry is also related to Thomas. Thomas is a Xometry company, and a lot of you are familiar with what Thomas does, or thomasnet.com as a global that is a global directory of manufacturers. So if we don't have it directly at Xometry in our quoting engine, you're going to find your supplier via Thomas. We want to be the first place you go to get custom parts made. And of course, today we're talking CNC machining. So I keep on mentioning a digital platform. What we call the digital experience for our customers is we call it the Xometry Instant Quoting Engine. The Instant Quoting Engine is a secure web-based platform where you can upload your technical file, digital file, and we accept most CAD file types, and it'll provide via AI and machine learning instant pricing and lead times on your part. So a few things happen, it'll interpret that part, say it's a CNC design part. It can actually predict saying, hey, we think that part's a CNC. It'll default to CNC machining, provide you pricing for the standard CNC materials like aluminum 6061. And then from there, you could go and click drop downs, configure your part, and go as deep as you need. If you need to add, specific tolerances, inserts, threads, tapped holes, part marking, bag and tag, finishes, CMM inspection, ITAR, facility requirements, they're checkboxes. It's like the easy button for sourcing custom manufactured parts. We offer multiple lead times from the standard to expedite to economy and international economy options, so you have choices along the way. And we meet you where you need us to be for your quality and facility plan. So we've gotten certified along the way. In fact, our last certification that we got was IATF 16949 for automotive part production, but we also do medical device, aerospace, spaceflight parts, and everything in between there. Long story short, we're a place to make parts. We love making parts for you, and we make it really, really easy. But today we're talking about one of those technology branches, CNC machining. So CNC machining, what is that? It is computer numerical control. That's what CNC stands for, in case you didn't know that. But it's a very broadly used manufacturing process. It is computer controlled. Someone who is programming a part for CNC machining is using CAM, computer aided manufacturing software, to interpret that design and turn it into code that'll be interpreted by that machine. When I'm thinking about what a CNC machine is, I like to think about a robot, but the arms aren't on the outside, they're on the inside. They're going to be moving the part body around, twisting and turning it as a milling feature or drilling feature is going and creating those cuts to produce your manufactured part. It's something that you know from industry. When you look at parts and you see that smooth finish on anything, even your plastic parts, it turns out that tool was CNC machined. If you look at stamped metal parts, those stamping and die tools, CNC machine components. This is the backbone of most manufactured goods, whether it's directly making those parts or building the tools to make those parts. And it's what we know as designers and engineers and manufacturers as something that is just a very reliable way to hit precision tolerances. You're cutting away from materials, so you're able to get smoother finishes versus process like additive manufacturing, where you're kind of growing based on a base material, and that base material kind of gives you what that surface finish looks like. This is actually a removal process. We know a lot about materials. I could, for example, order 6061 T6 aluminum alloy from about 2,000 vendors and have very high levels of confidence that I'm going to get the material with the properties that I require based on my engineering needs. And it's just got that track record, and it also has a lot of redundancy. Xometry's manufacturing network allows us to tap into open capacity, both domestic and globally, depending on your requirements, and start jobs right away. So lead times on machine parts can be as little as a couple business days, And of course, when you add, complexities, finishing, secondary operations, that adds up, quantities will add up. But we can start with very quick and then build upon what your needs are. So, you know, talking about that, a lot of times you'll hear the vernacular of 3, 4, and 5-axis machining. And Steve, love to talk to you a little bit about what that means. If you could explain when we're talking about axis
Yeah,
machining.
so when it comes to axes, that's the number of axes that you're actually programming in the machine. So a three-axis part, you're programming in X, Y, and Z to where you can get everything in an X, Y, and Z motion. When you're talking about fourth axis, you're adding a rotary in there to where you can get to compound angles a little bit easier, less setups when it comes to fourth axis. And then fifth axis machining, you add a second rotary to that. So now you have 5 axes that you're completely programming separately. This can cut down on setup time, but can also improve machining cost as well when you get into 4 and 5 axis.
Yeah, and I think you mentioned like cutting down setup. So when I'm building a part in machining, right, I'm fixturing in place. And
Correct.
then I'm moving, and whatever my tool can reach and access for what makes sense for that operation, we call that an up. And then you'll change your fixturing around. Sometimes you need to make tooling to hold that for a second op or third op or fourth op, etc. And if you have features like this design here, where these holes are on plane to each other, but they're off plane to the rest of the holes, and same on these holes on this opposite side, if you add a twist, right, add an axis, then you could actually make those features within the same op as the other features there. And then fifth axis, you could do even more with that. But yeah, they do drive pricing as far as like higher overhead of machines. But to your point, yeah, they definitely can, depending on the geometry, it may just make sense to use a higher access machine for specific features, especially if those features have some sort of GD&T relationship, so a dimensional relationship to themselves as well. But yeah, this one is kind of hard to see on the image here, but each one of these holes is actually annoyingly at a different plane. So a little bit of tilting and moving, which makes this a true fifth axis component here, because you would have to do a specific operation and fixture for every single one of those holes if you're just working in a 3-axis kind of like top-down motion on those parts. And yeah, tools of the trade. So we are spinning tools in CNC machining. So we're using tools to remove material, and each one of these has their different. I guess each one of these will be able to make different feature sets, and we're going to go over some of the principles of those feature sets in the next few slides here. But see if you want to go through some of these, so, we could go from left to right on just end mills going on.
Yeah, so all the way to the left, that's just a standard end mill. It's got a flat corner radius, no corner radius at the bottom. This would be used for machining pockets or voids down inside a part. The next one is just a regular twist drill, like a jobber twist drill. You could make through holes or you can make blind holes. The next one would be a tap. So that would be ran down through a hole after the drill to machine the threads in. The next would be a key seat cutter to where you can get undercuts and underneath features. And they come in all different shapes and sizes. The next one would be a ball nose to where you're actually using that to surface a feature. So down inside or on the outside of parts, you can use that and do micro step overs to actually put features, kind of like flow features into things.
Yeah. And
Um,
by the way, I'll say like this is my PowerPoint skills, so keep in mind this would usually be rounded in the real features here. This is just my extent of being able to make a PowerPoint or slide deck to show off these features. Yeah.
Yeah, and then the next one would just be like an edge break tool, a chamfer tool for breaking edges so that there's no sharp, edges for somebody to cut themselves on. And then the last tool, that's what we use to hog a lot of material off. So that's what a face mill, that would be to take a lot of material off the top of something or the bottom of something to bring features closer to their intended design.
Yeah, and operationalized, when we were building the slide deck, I put this at the end, but really this is often the beginning. So when you're, you know, when you're doing details, you may be using an end mill to go and create those paths of, to do detailed cuts and kind of get nooks and crannies. But if you just have a broad, flat face, you're just trying to hog out material, save time in your machine, you can see this kind of swirl pattern looks a lot bigger than the swirl pattern on this side. And this would be like a face mill clearing off that material going back and forth. And what it does is it saves that overhead time on the part manufacturing for that operation. So, and time is truly money. In this case, time is cost on those parts. And that's a great segue. So we're moving into this is I think the next couple slides are very, very important, especially from the design principles of advanced design principles for CNC machining here, where we want to talk about what's common. And this is typically what we recommend in our design guides versus cost driving features. So it's never a question of can you make it at Xometry. I have 5,000 jobs. We can make parts of any type of geometry, shape, or size. It's just more about how much cost does this need? Like, are there special features? Do I need to add secondary operations? So, when you're thinking about Xometry, don't think of us as a single shop when you're asking questions like, can you do X? Or can you cut X? Like 99% of the time, the answer is yes. The real thing is, does this design incorporate risk or additional features that you may not be aware of that's going to drive cost, lead time, or risk to the manufacturer of those parts? And yeah, let's start with the first four here. These are some of the common ones that we have. And Steve, I was thinking for this one, I'll kind of talk about the features, the recommended, and
Yeah,
then you
sure.
could talk a little bit about the cost drivers and how you see that through your machinist side as well. But the first one is a common one we get asked all the time about, which is wall thickness. I'm going to give you the recommended minimums, and I'm going to, I wish there was little asterisks that are appearing all over my screen right now as I said the word minimum, because keep in mind, minimums are like, you shouldn't make the whole part to a minimum feature side. That would be like going to your auto store and buying brakes at the minimum thickness. Like, you want to use minimums where you need them, but you don't want to increase risk across your parts. So minimum recommended size for metals is about 30 thousandths of an inch, 0.030 inches, and plastics typically double that for that. And that's because of some vibrations and work holding needs for plastics, like they're a little more wobbly by their nature. But yeah, cost drivers for wall
Yeah.
thickness.
Yeah, so cost, anything that's going to be a real thin wall, whether it's in metal or plastic, is going to drive up manufacturing costs because we have to slow the machines way down in order to achieve the correct surface finishes. It might even be a different approach of the manufacturing altogether. But at the end of the day, it definitely drives costs because it slows the machines down.
Yeah, absolutely. And we, know it's interesting, the internal corners here, we have a 1 to 4 diameter depth ratio recommendation, which is, again, like what can I cleanly cut into with my end mill? And we also have a recommendation to not make that diameter the standard size of an end mill or drill, make it a little bit bigger, because that allows you to cut in and cut around without with an even engagement of the turning tool. So we have this like kind of little bonus, like give about 30% bonus diameter on these on internal corners. But yeah, one of the most common things we see is leaving sharp.
Yeah, so leaving sharp corners, you got to remember our cutting tools are round. So you almost have to leave some type of corner radius in there, or you're going to get into an EDM or broaching operation, which is going to be a complete different machine. It's going to be another setup, which is definitely going to drive up cost.
Yeah. And if you have a smaller radii in there, right, it may look kind of rough and chattered because the
Correct.
tool just is overextended.
Correct. Yeah. When it comes to cost drivers with manufacturing, it's machine time and tool wear. So the more they can keep that tool engaged and taking the same metal removal off at the same amount of time, the
Mhm.
longer tool life they're going to get out of that.
Yeah, absolutely. And this is actually, by the way, I liked when we were making this slide together. I even had this question for you, Steve, and you helped give me guidelines. So thank you so much for this. Floor radii. So floor radii, I'm
Yes.
going to jump back to this real quick. So this is end mill creating pockets, right? And you can get
Yes.
end mills with rounds on them. So recommended is either just leave it, don't radii at all, because you can cut flat on a floor in a pocket, or 20, 30, or 60 thousandths is common for a tool. And don't over tolerance that, but that should be, your we call that like a reference dimension, for example, down there. And we would be able to mill that out with a standard tool without having to, custom surface that radii.
Yep. Yeah, the main thing when it comes to floor radii is just keeping stuff standard. So your standard end mills come with a 10, 20, 30, 60 thousandths radius. So you want to keep it a standard tool radius. Once you get into like, 50, 100,000, that kind of thing, then we're actually surfacing that, which is going to drive machine cost up and machine time.
Yeah, absolutely. And edge breaks, actually, I saw someone had a question on edge breaks as well. And Justin asked this question. We'll cover edge breaks in like two sections, but this is section one of edge breaks, which is you don't need to model them. We will we do edge breaks as workmanship. It's just part of Xometry's manufacturing standards on machine parts. We don't want you to cut yourself when you handle machine goods, so we actually do edge breaks there. If you're designing or calling them out in the drawing, 45 degrees is standard because you could use a standard tool to create those features. As the second that you don't have that, you have created a feature, not an edge break. Like if you created something that needs to be modeled in the design and produced. Um, Typically, best practice is not to exceed 30 thousandths of an inch for edge break, but you also don't want to tightly tolerance that if it's just something that's edge break, because we don't want the rejection criteria to be like an edge break that's off by like a thou or something like that. So
Yep.
cost drivers is anything non-standard. I kind of covered that, but yeah, don't tolerance it too tightly there. I'm gonna go to the next one here. So continue the second page here is actually mostly around drilled holes and pockets here. So when I'm using a drill, so versus an end mill can go down, plunge down, and also move left and right, up and down in order to produce cut pocket features. A drill is creating that round hole straight down. So I can have a longer aspect ratio to it. We want to keep it less than 1 to 10 diameter to depth ratio as a basic guideline. You can't push it a little bit, but let's talk about recommended. But there is, specialized requirements. And Steve, you actually like, what is a gun drill? And like, when do we use
Yeah,
that?
so gun drills and then long aircraft drills. I mean, if your application needs a hole deeper than the 1 to 10, then obviously there's tools out there to do it. But you're getting into custom tools, custom machines at sometimes. If you're doing really, really deep gun drilling, then it's going to be a custom machine as well. So that's going to add another operation and more cost to it.
Yeah, absolutely. If you ever have those concerns, you can talk to our team. We'll spin the CAD and kind of give you, some sound advice there. Um, so pocket width to depth, this is actually very similar to the internal radii, that 1 to 4 depth of width ratio. Think of it the same way. Like in this case, if we were talking about the radii back corner on the previous slide, this is just expanding that throughout the part. Just know that if you have protruding features, so say I have a little boss, or for example, like on this design here, I have this little inlet. So the machinist chose to use the same end mill that can fit inside this inlet and create those features as well as the rest of the part. At a one-off, that may be something that's completely fine to do where they're not changing out tool sets for the sake of convenience, but that can drive the time to create that pocketed feature because you have to reduce the end mill size. So, reduce size of end mill means I just have to, cut more, do more paths to actually remove that material. Thread depths wise, we recommend less than 2x the diameter for the threading itself. So mechanically, only a few threads are actually doing work at any given time on a threaded hole with a threaded bolt style. You don't need to fully thread a hole. So we uh, we do like through holes in it, but as far as like what you're actually threading, to about 2x of diameter or less is probably the best guideline. But you do add cost and risk, right? To like breaking taps, for example, on longer threads.
Yeah. And the main thing with threaded holes, if it's a through hole, you can thread completely through. That's totally fine. But your fastener is only going to be engaging about 1.5 to 2 times diameter. always leave a little bit of extra room below the threaded holes as well for
Yep.
the tool itself. The tool's got about a 30% taper on it. So about the first 30% of the diameter, you're not getting full thread engagement anyway with the tool.
Yeah, absolutely. So these ones are very closely related there. That additional hole depth will need that. And also if you're using inserts, so a helicoil, a key insert, something that matter like brass screw to expand inserts, all of those, you want to have clearance below those inserts so that we can install those, especially like a helicoil, right? I need to actually first pre-tap that hole, then install that helicoil to it, so I can't have a bottoming thread there. When you have a need for a bottoming thread, maybe it's a geometry requirement, we do need to use a tool like a thread mill to produce that, which may drive some cost on that feature itself. So on that note here, this is a thread mill, by the way. You can see that little, imagine that tap only is one little groove, and you're using a computer numeric control to tell it what to do and make your custom thread. But yeah, Steve, this is a lightning round if you want special features. So
Yeah,
what's yeah, go
so
through them.
special features. This would be stuff that's not your normal typical lathe or mill machining. So gun drilling really deep holes. Reaming of holes are just tight tolerance holes, which is another tool involved, but it does drive cost if you don't need really tight tolerance hole. Any kind of grinding is going to drive cost. Porting, which in the side view of the tools, that's a porting tool right there. So you're actually putting in a form. It's a form tool that's putting in a bunch of different angles and diameters at the same time, but it is a custom tool.
Yep.
Slitting saws, they're very slow. So any kind of like fin features and stuff like that. Most machinists are going to use a slitting saw to cut those. Key seat cutters, which is a normal tool, but at the same time, it's getting up underneath of certain features, so it is going to slow the actual machining of it down. Extended reach tooling, so anything that's super extended, like a long reach, it's going to slow the machining process down. EDM, wire or sinker EDM, is where you have to have like a square corner in a hole or in a pocket, and you can't have a radius. We'd have to go in there with an EDM machine, which is another whole different process. Same way with broaching and gear hobbing. They're separate processes to achieve the right features.
Yeah, and this is something again. The question isn't can you at Xometry. It's more about like is what are the requirements of that print. So for example, grinding is fairly common for us on harder metals. But you may actually be able to activate our team to review this based on how you're configuring the quote in the instant quoting engine. Usually a ground feature may have a surface finish that is beyond like our drop-down menu, or more likely it has a tolerance that's sub 1,000th. So on Xometry's website, you could select down on your tolerances that and we want you to choose the tightest tolerances on your drawing. If you have tolerances that are below 1,000th of an inch, so plus or minus 1,000th, what it'll move the quote to from auto quote stance, it'll go to a manual quote review. We want you to attach your technical print, and a lot of times we're going to read between the lines. In order to achieve this feature, we're going to need to build the net shape and then grind to finish that feature off. Or sometimes you have a hardening step in there, so it's net shape, harden, post grind to spec, ship to customer. So we make a lot of parts here. Sometimes it'll automate for a manual quote review as you're specifying your technical needs on our instant quoting engine. Sometimes for things like gun drilling, like extra long holes, those type of features we want to we like if you reach out to us, raise your hand, we'll take a look at your quote really quickly and get back to you with some feedback if we need to change anything. So that was kind of like a speed round of design tips. Like we're making those parts. Now, how do I, make my drawing? Like write that love letter to your manufacturer that you can give to any manufacturer. And if they're reading that along with your CAD file, what you know that you'll receive what you're looking for, right? That's the biggest thing you want to do is we want to make sure that you have a transferable communication between suppliers. And the first thing is just making a good technical print, make a great drawing. Typically we are CAD derived, so it used to be tolerancing every feature was a common thing because there was no CAD and CAM uh, building up to a CNC program, which is the typical steps now. It used to be machinists, looking at the print, seeing every single measurement, and making those features using manual tooling. Well, now you really only need to call out what's special about the part because I already have your 3D file. If you have a title block, you could call out very quickly using 2 decimal place, 3 decimal place, 4 decimal place, a tolerance range for those features if they're important and you want us to measure them. But a title block, which is going to be this portion of your print right there, can help cover a lot of those features without you need to put a plus or minus on called out tolerances. We also recommend, and I have another slide on datums, calling out where your datums are, if you have any, and you're using GD&T, and building your dimensions off of those datums and tolerancing off of those datums, because those are essentially translating to how our machinist is going to set up your part and how our QA team is going to measure your part. And again, we'll go through GD&T, but the most important thing for me is to know that GD&T is applying a tolerance methodology to parts that go into other stuff. When we talk about making great drawings, making great CAD designs, we want to think about how transferable that is without you having to, tap the machines on the shoulder and say, "Oh yeah, it fits in this. I'm going to give it to you right now, and can you make sure they fit together really quickly? And if they don't, just adjust the machining setup really quickly for me." Like we want to move away from that and move towards, methodology to actually make, things fit together using your technical prints. As I mentioned, we have your CAD, we have your drawing. We are going to measure with our inspection reports based on what you call out. So calling out everything that is important is what we want to see on your drawing. But if it's something where it could be CAD derived, it's just, is the feature there or not? You don't need to call that out in a print itself. Over tolerancing can drive costs because you're essentially putting work in that spot for our inspection team to measure. And also, I see this a lot where a print is redline, but the CAD is not redline. We don't want to do anything that may cause an accidental mistake on the machining side downstream, right? So they may be setting up their CAM program with that CNC CAD design, but if a red line says move this hole over X amount on the print, that may not get caught right away, and we may make a feature that's wrong from that print. So just always take the extra time, take the extra 5 minutes. If you have a red line on your design, update the CAD or vice versa. Make sure that those two match going along the way. So yeah, Steve, if you want to go, like, I think that, like, I'd love talking to you about like how a machinist thinks about GD&T. But let's just talk about datums and GD&T really quickly here.
Yeah, so datums, geometric dimensioning and tolerancing, like Greg said, it's a system to make sure things fit together. Um, when a machinist or a programmer first takes a look at your print, at your model, they're gonna note the datums. Your A, B, C is your main datums. That's what everything's gonna be programmed and machined off of and then measured back to. So make sure that you're designing your datums clearly to the design intent of that part, if that makes sense.
Absolutely. And they should be at least a physical feature on the part or something that is kind of captured. Like, so for example, an axis can be a datum, but what we don't want is part datums that are in some theoretical space. So say, for example, this has a curvature on this face here, and the center of that curvature is, 3 feet away from me. We will like that's very hard for a machinist to theoretically set up and make a parts based on those data. So you do want something like, for example, on axis here. That means that you could turn down and produce features using a lathe tool to produce features that are on axis and true to that datum. And this is just really important. Like setups matter when you're setting up those parts, and measuring and building features off those datums makes it very easy because not only are you the engineer designing parts with datums in mind, the machinist is setting up those parts with those datums in mind, and the inspectors are inspecting with those datums in mind. So it is a universal tool. that gets you all the way to a shippable component. And this is a little cheat sheet. It will be like an 8-hour webinar if we actually went over every single GDT call out. And there's lots of services that also will do training on this. But just an example of like why you may use the GDT call out here. And I'm moving my, if you see me looking around, it's because I'm moving my camera view around so I can get, because I have so many features out here. Angularity is going to be for things like just checking like the angle of a feature, like angled brackets. Circularity, think about a bearing, something that's going to be fitting in something else that needs, a circular feature. Concentricity is going to be two circles and how they relate to each other. So I have this part beside me here. It has 4 threaded holes on the bottom. It has 4 slightly larger holes up top in this array here. These holes may or probably have a shoulder screw that's coming up through this feature and shouldering up here. So I may want to measure these as a concentric or even cylindricity, which is the third dimension of that. So cylinder to cylinder, to make sure that those are lined up with each other as I measure, and that way I know that when I get this part into my building, I can install my my shaft or bearings immediately and get a functional part out of it. Flatness is a lot of times datum A's may have flatness. So datum A's are typically like a large planar face on a datum. Parallelism, think about making a rail guide, making sure that each side of those rails are straight and parallel to each other. Perpendicularity, the opposite of that, is this thing off of a right angle? And this is a way to measure and give how much degree of wiggle you can allow before it's a rejected component. Again, this part is just a famous part for me right now. Positional tolerances. So these 4 holes may be installing into something else entirely. What's really important about that is not necessarily are these 4 holes exactly where they are, this way. It's more that are these 4 holes important in relation to each other. So I may put a positional tolerance for these 4 holes, saying the relationship of these holes to each other is important to this degree of freedom. And that'll allow me to design a part that installs with the other thing that you're making. So that's position is probably one of the most common tolerance, GD&T tolerance we see. Profile is going to be looking at a surface. So say you have a keyway or a contour feature, airfoils, really good example of that for making that. And there's both the line, the 2D version and a surface version. Run out would be the straightness of an item and how that may wobble or change or move along the theoretical straight of those parts. And then we have, I just said straightness there. Straightness is going to be like the linear dimension of that. And then symmetry is for mirror features going through. But these are the symbols for GD&T. A little bit of whys behind them. And like I said, we could be here all day talking about GD&T. But the most common I typically see position, profile, flatness, concentricity are usually down there, parallelism as well, and perpendicularity. Now, that being said, there are consequences to when you're tolerancing your parts. We measure parts at Xometry and we measure to your design. Um, we have lots of selectable options for inspection reports. If you choose a formal inspection with report, you're going to receive an inspection report with your part in the mail as it's delivered to you. We also have options for more advanced inspections, including like CMM inspection. CMM is a coordinate measuring machine, which is kind of think like a CNC machine where it's cam driven. It's driven by that CAD file. But in this case, it has a little red touch probe that is pinging out points and spaces. So when it touches an object, it'll record that point in space. And it's very good for measuring a lot of these GD&T callouts, like true position, cylindricity, profile features. In fact, surface profile features, you absolutely need a CMM in order to measure those features correctly, or use a vision-based scanning system, but CMM is more popular there. It does add cost, but just know that if you do have those callouts, you do need to ask for the inspection equipment that can actually measure those. And the most common thing I see here is the stuff highlighted in yellow here. I've seen a big trend in this happening on drawings where you have this one little note. All dimensions not shown are to be considered basic. All surfaces are subject to following tolerance, and it gives a surface profile of your entire part. That means that we need to put this on a CMM, which is a higher overhead, more costly device, in order to ping out features all over that part and figure out, do any of these features deviate from that 0.010 to the datums of a surface profile. So you've added cost. It's not good or bad, but it does add cost by putting that little note in, because you do have to request for CMM for those. By the way, I saw Philip had a quote saying you have to cater for us Europeans who are metric. Good news is on Xometry.com we have imperial and metric conversions. So sorry about talking in thousands for you all here. And now I have more thousands. So getting out of GD&T, just I have a really quick slide just talking about bilateral, unilateral, and limit tolerances. So sometimes it's just distance, like how far away is that feature to this feature, or how wide is that feature, for example. Generally, bilateral tolerance is what you see most of the time. Sometimes you don't even need to put bilateral if they fit your title block. So you can just call out the feature size. And if it's 3 decimal places and your title block says 0.005 or 0.012 millimeters, my friend, or 0.12 millimeters, you will, we already know that. We already know that we can refer to your title block. If you have something differing than that, like a plus or minus 2 thousandths, for example, on a tighter tolerance feature, you could use the bilateral tolerance. If you have a fit where it's like, hey, this thing can't get bigger than this because it's about to fit inside something else, and then that's when you use something like a unilateral tolerance. So say a +0. It can't go beyond this. It can go before that. And usually the mating part will have the opposite of that. So if it's a +0 on, a pin feature, the slot feature will be, a -0 with bonus tolerance to that. Um, and then limit is kind of another way to write bilateral, but it's usually more inspector focused because it just helps them kind of quickly check, is it between these two? But either way, I always recommend, regardless of these, all these are using 0.625 as a nominal in your CAD design. You will reduce error by designing to the nominals, for your tolerances. Steve, do you have anything to add there? Anything you've seen?
Yeah, it actually, so my like an example where I've run across is when I'm programming parts and there's plus and minus dimensions. That means I got to use different tool paths for each of those. Where if I could use one tool to complete a bunch of different features, now I have to break it down into 2, 3, 4 different tools because I'm holding different cutter comps and different programming paths to hold those. So nominal modeling is definitely preferred by the machinists.
Absolutely. I have a burnt hand on stove story of a minus minus tolerance that gave me a bad day. Where minus minus tolerances sometimes happen with fit items. They're kind of like a way of writing unilateral tolerance, but the challenge with the minus minus is, say it's 0.625, -10, -20, right? You the design that you receive is still at 0.625, and if you mill out that feature, you could always make a hole bigger, but you can't cut a hole smaller. And so the part is rejected. And in this case, this was one of those where the print was kind of rough. So we thought it was just a like a little a scanning error that it looked like minus minus, but it was not. And that brings me back to one, design for the nominal, and going back to also that note, ensure you're drawing in CAD match, because sometimes minus minus comes in when someone makes their design, they think it's correct, then they actually fit it in, realize, oops, I got to change this really quickly, for like a shaft fit or something like that. So all they do is redline the drawing, and they just scratch out the tolerances, put in like a minus minus or something. But yeah, it doesn't mean, like, technically we're in the wrong if we don't hit your print as it's called out. But unfortunately, prints can be deceptive if you're not matching your CAD to your print. If you're doing a red line like that, it's very easy to make that mistake. So you're introducing risk by design with those type of features, which is why we're giving these tips today. And some more drawing tips, go through these a little bit. And again, I've seen questions come in, so thank you so much. Keep on asking those questions. But make sure to fully define your holes and threads. So not just I want, a 1032 here, But I want I want this with this, I want a 3/16 hole UNC-2B, which gives me the inspection requirements for it. And this is a through hole, or I have a hole that goes down, for example, this hole here goes only down, 0.038, in this design. That's that information is invaluable for us. It allows us to inspect it properly. If not, we're going to go back to best practices, but that may not be your intent. So fully defining holes is very important. One thing to note is on a drill relief, you don't actually need to throw a drill relief in design. If your thread wizard has it, no problem. But I've seen some on some larger features that could actually be either drilled or pocketed. You if you have a drill relief in, we actually may surface that feature. We actually may think it's a feature of your part and surface it in. You could always call out, put a little line to that feature on your print and say, okay to have drill relief. That's fine there, but you don't always need to design it if it's not necessary to your part. Um, we talked about thread milling. If it's a truly unique type thread, we may want to see that modeled. Otherwise, a call out is sufficient. That hole should be the drill diameter for that threaded feature because we need meat to cut out of. But we do not recommend modeling threads in the design. This is just I feel like I'm just giving you all these warnings, but things that we've seen rejecting prints that are unnecessary, super tight tolerances on counterbore features, head clearance features that all they need to do is have extra relief because of a screw head, for example, and they have a extremely tight tolerance and a whole part's rejected because it's out by, a thousandth of an inch or something. Just loosely tolerance where it's non-critical, tightly tolerance where it's necessary. And we already mentioned the edge breaks. A nice call out I like to see on edge breaks is I like both. I personally prefer machine breaks. So in my notes section, I'll say machine break all corners and sharp edges. I also like this, which is a not to exceed. So that gives freedom for the machinists and the inspectors. Just know, like, as long as it's below, 0.030 inches, you're in the safe on it. Because this, again, is to prevent you from cutting yourself. Machining is going to be something that just makes it more consistent across. But that's what we have here. Steve, you got any notes?
Main thing with the edge breaks is don't over tolerance them. And like Greg said, you don't have to model those in. Just break all sharp edges, machine break all sharp corners and edges. The machines and our cam systems, that's just a click of a button to add
Yeah.
those edge breaks in. Where if you're actually holding tight tolerances, now you're creating a feature, and that's a whole different toolpath.
Yeah, that's something newer on cam, which is really nice. Is I know I saw some modeling cam in Fusion 360. It's literally a checkbox now, which is pretty
Yep.
nice. I'll go quickly over these because I do want to get some of these Q&A here, and please keep on asking questions as we go through. Something important to note is we serve every industry at Xometry, and we have parts on space. We have parts on the moon. We're able to make a lot of different features, but just know that if you do have a flight or space flight component, talk to us. This is not an auto quote behavior. Like we want to make sure that you're using the quoting engine as much as possible, but this is where you get our solutions engineer on board. Same for medical devices, same for automotive production. We are here to help guide through because typically it's not just can you make the shape, but the documentation trail combined with that to make sure that it fits that highly critical application. And that's where you bring our solutions engineering team, whether it's reaching out to your sales lead or reaching out to Xometry's support to get in contact. You can still use the quoting engine to set up that quote, get it configured as much as you can, but just make sure that we're in the conversation before you press buy for, again, space flight. It's just very important for us. I have a little case example there. We have a great case study where we actually did unibody machining for the Eclipse system on the International Space Station, which is a CO2 scrubbing system. And they had a challenge where NASA did not have the machining capabilities to actually produce this part. They were thinking about welding together, but they had a lot of challenges in qualifying that weld. They asked us about it, and we said, well, why don't we just mill it from billet? And they're like, you could do that? And we said, yeah, we can. And so now we have, parts on the space station that are part of their life support system. And so there's a lot of capabilities that we have that we can offer that are way, if you, even if you have your own shop, we may be able to do a little bit more and help you out. And scaling up, I just like to show this graph. I made this graph. I think it's pretty, but really we're talking about CNC machining, mostly metal CNC in today's webinar. At some point, as you're scaling up, we have other options to help you move into higher level productions. And I just like to show you how this looks in the continuum of manufacturing. CNC brings you really far, really precise items. As you move up, there may be some cost savings moving to progressive items like die casting, for example, stamping, metal extrusion. I don't have it on here, but like metal injection molding. But just to let you know, like there's a world in production outside of machining, and we're here to help you there as well. And as always, we have resources, webinars like today. We have recordings of those webinars. We have great design guides, xometry.com/resources, and case studies like the NASA one we have here. And we also have this very cool poster. We'll send this to a link to you as well. But this is a downloadable poster that you can print out with some great CNC design tips, including what Steve and I talked about today. And with that, though, I see questions, so I'm going to jump into here. And we got Megan Conniff from our team here, who's a marketing guru, and will help us through some of these questions. And my quick promotion on the instant quoting engine is, if you haven't tried this out, upload your files. I got this code right here that you could use to get a discount on your next order. And yeah, we'd love to do some work for you all.
Excellent. Well, thank you all for submitting questions. We've got a lot in here. We'll get to as many as we can. Steve, first question is for you from Chris. What are the most common issues you see with manufacturers' ability to interpret design intent from technical drawings? What are the biggest issues with technical drawings for high precision parts with GD&T?
So, not clearly defined datums would probably be the biggest. That or datums that are, as like Greg said, that are out in space. Keeping your datums to actual measurable points is going to help the manufacturer out greatly on that.
Excellent. All right, next question. Does Xometry offer part review for cost optimization?
Yeah, so that's where our solutions engineering team comes in, and that's been part of my role as well as the role of our team members. We have experts in every discipline of our manufacturing, continuum that we offer here at Xometry. So usually that comes hand in hand with DFM. So we do a lot of design for manufacturability review, and the cost drivers are usually one-to-one on that. Sometimes we can also take a look at your quote and kind of figure out what's driving cost and lead time. A lot of times, if you have something in, a specific need to hit, X cost or X lead time, we may be looking at first, like, what can I trim on my secondary finishing? So if I have a powder coat step or I have something like that, that may add, 4 or 5 days to my part that we could trim off if it's applicable. But yeah, that's what we're here to do. We're here to help. Beyond the quoting engine, we have humans in the loop that are ready and available to support your needs.
Great. Next question from Josh. I think you said you prefer drawings without plus plus or minus minus tolerances, meaning you'd rather have the nominal as the low high end and the single direction tolerance?
Yeah, so I like the limit tolerances for those personally, and for your design though, you want to build to the nominal of that, whatever's in the middle of those features. The reason why we talk about design toward a nominal is, say I have a 0.625 plus 0, and it's modeled at 0.625, and I'm machining to 0.625. A slight variation on one direction can scrap your entire part. Now, if you have that 0.625 plus 0, minus 10, and you modeled 0.620, so you model to the middle of those, a slight variation won't scrap your part. And that's a difference for you. It could be a difference of business days of lost time. Like, we're still going to make your part right, but by modeling to that nominal and making clear and readable drawings, it's going to be much more useful for both you and those who are interpreting that to make your part successfully on the first run around.
Next question is from Chris. Should I be applying datums based on my part's function or how my part will be inspected?
Function.
Yes.
Definitely function.
A good way to think about it is like, where's your part installed, right? So if I say I have a part that's sitting on a table and nooked up against like another thing in its assembly, tables datum A, B and C is the thing that's nooked up against. Now, say on that table it has a whole feature that I'm screwing this into. Well, then I have a true position profile tolerance for that whole position because I know like this is relative to the table and then nooked up position. That hole should be here. And so like that's how you have to think about it. Is like you start with function first, and it leads into better QA. So it's a foundation for making good prints and good design intent towards your manufacturing needs.
Next question is from Ed. Is it practical to do a prototype in a cheaper material, i.e. plastic, to verify fit, then do the final in the actual, say, aluminum material?
So funny enough, aluminum's cheaper than plastics most of the time because it's easier to work hold and it doesn't dance around when you're cutting. So you may find 6061 T6 is kind of the bread and butter material for running. We do have other ways to prototype though, including additive manufacturing 3D printing. So you may, for example, use a process like FDM 3D printing to build a part that you're eventually going to be machining. I like using FDM because the design rules are basically one-to-one with CNC machining, like the wall thickness guides and everything else for that, or selective laser sintering as well. But those may give you a low-cost way to quickly iterate and change your designs with still a functional enough part where you can get tested through, and then you can invest in the machining once you're ready.
Excellent. Next question, do you have a template for technical drawings?
We actually do. So we have, if you search the Xometry site, how to make great technical drawings, we have a um, we have a really nice guide that goes step by step on things that we like to see, including a lot of what we covered today. And linked to that, if you are running SolidWorks, we have a solid draw template that you could download and use that as your own and take out the Xometry logo and whatnot, but you can use it as your own if you don't have one standard already.
Next question is from Eric. Any tips about external part size versus stock size? For example, what is the maximum thickness you could cut out of 0.25-inch stock, looking to minimize material waste, machine time, and cost?
Yeah, so it depends on your surface finishes. So your materials are going to have a certain tolerance from the mill or the manufacturer of the material. So if you need something that's got to be close to 0.250 thickness, then you would almost have to order something at like a 0.375 and machine it down. So it depends on surface finish at the end of it.
Next question is from Fabian. What are the different capabilities between CNC machining and metal 3D printing?
Oh yeah, so we're talking about additive versus subtractive manufacturing at that point. It's about access to features is the first thing you have to think of. When I think about subtractive, I'm removing from stock. So I'm thinking about kind of line of sight features. I can see every feature that's created on this part, and those would be my operations or setups to create those. So my design mindset is about subtracting and accessing those features. So say, for example, this had a small internal channel that made a curve around. I couldn't hit a straight tool and create that curve. Where additive manufacturing is growing parts. I'm building from a base and growing up. So think like your coral reef, right? Coral doesn't just like grow in the middle of the ocean, right? It's attached to rock or substrate and then building out based on its function. So when I'm moving to additive manufacturing, I have much more freedom to build organic shapes and create those features. So they're both ways to make metal parts, but my design is very different. The other thing I noticed that when I'm removing material in CNC machining, I'm working. Any hogging out material, that's work, that's overhead, that's cost of part. In additive manufacturing, if I leave material in a part, and I make a brick, I have to make all that brick. And so that's work. So a lot of times when you get an additive component, it's going to be on a diet. It's going to have lots of coring features, internal channels, things that are going to reduce that weight and bring it straight to its function. So your design intent kind of flips around versus what you do with machine parts.
Next question is from Kyle. Does putting GDTT on a print automatically drive up cost because it may now require use of a CMM?
So my short answer is no. It won't. But if you are putting GD&T with things that have a three-dimensional reference to them, so concentricity, for example, where I need to actually create like a data set of like essentially imagine creating ping points around this feature here. So and then I have to compute from that what the central or what the central cylinder axis is, like that type of stuff. Surface profile, where you need to create a computational model of like the theoretical center of something or the theoretical surface. That's going to require the CMM requirements. A lot of things can be done manually. I put on that slide deck around positional tolerances. I put true position as a CMM need. It's not necessary. They've been doing true position since before CMMs, but the more holes you have in an array, the more I'd recommend it. Steve, I'm not sure if you have any tidbits on that as well.
Yeah, no, mainly like profiles, cylindricity, that kind of thing, where you're getting into a three-dimensional type of measuring. That's what's going to drive a CMM inspection.
Great. And now we are at 2 o'clock, so we're coming up on time, but we have another question here.
Sure.
Do the same manufacturers make my parts when reordered?
Yes. So Xometry, we are a manufacturing marketplace. We have a variety of manufacturers, and we use AI machine learning to matchmake, to pair the scope of your work with those suppliers who could do that work best. What your parts are tracked with an internal Xometry part ID, and we have revision control. So if you're making the same part but you have a revision, you can revise that part on our site in multiple locations. But when you do the reorder, it becomes an exclusive offer for the prior supplier. It's a win-win. Like you get the parts that you expect, supplier gets parts that they're familiar with. So it's a really good feedback loop that we encourage and we have embedded in our infrastructure. All right. Well, Megan, thanks so much for being our Q&A MC, and Steve, thank you so much for being a co-host. I mean, this is just
Yeah, no problem.
I love these things. I learn as we're also preparing for these events. So as always, it's always appreciated. And just know these are team members here at Xometry. We have a lot of expertise in-house, no matter what process we offer. And we have a lot of convenience with our instant quoting engine. But if you do need to have that extra step, DFM review, talk to your rep, talk to our team members. We're always happy to help. And thanks so much for attending. Have a great day, you all.
Building modern machines, devices, cars, or even bicycles requires a complex manufacturing supply chain. You constantly need to vet and maintain your manufacturing network, which takes time, money, and effort. Ultimately, this distracts companies from doing what they do best, building and manufacturing products. This is where Xometry comes in. We have built a leading manufacturing network with over 10,000 vetted manufacturers globally. Xometry connects people with big ideas to the manufacturers who can bring them to life. With our AI-powered instant quoting engine, you can get quotes for your prototypes and production parts in just a few clicks. You can choose from over a dozen manufacturing processes and hundreds of material and finishing options. All you need to do is get your quote, place your order, and Xometry takes care of the rest, from selecting the most experienced certified manufacturer to performing quality inspections according to your required industrial standards, and having the parts delivered to you reliably and on time. Xometry makes it easy for engineers and purchasers at both small and large companies to tap into global manufacturing capacity and create resilient supply chains. From prototypes to high-volume production, build your products with Xometry. Xometry, where big ideas are built.